Okay, next we talk about supervised learning. Supervised learning, as we mentioned, is we look at the class label ahead of time. We say, okay, these are the normal, these are the tumor. Let's look at them. What are the biggest differences between the two groups? And then use those to predict your new sample. And so you can imagine we look at just the differentially expressed genes, right? That's a very simple case. You look at all the differential genes, and then when you have a new sample, look at the expression level for this new gene, and then you try to make the prediction. So very often, in order to make sure that you don't overfit the data, overfitting is that on your existing data, you've trained some classifier that perform perfectly on your existing sample. But when you try a new group of data that you haven't seen, it does really poorly, and that's really overfitting. So you can estimate, in order to make sure that you don't overfit, very often you do cross-validation. Yeah, so you use cross-validation to assess the performance. And there are a number of ways to do this cross-validation, depending on your total number of samples. Supposedly, you don't really have too many samples. You can do this leave one cross-validation, which means, say, you only have 20 patients. You take out one patient. This patient, you know initially what its disease stat or healthy status. And you use the remaining 19 samples to build a classifier, to make the prediction, and you test on this one guy that's taken out. Or you can do something called n-fold cross-validation, which could be 3-fold cross-validation, 5-fold cross-validation, or 10-fold cross-validation, which means you divide your original data, say 3-fold cross-validation is you divide your original data into 3 of roughly equal size. You use 2/3 of the data to do the parameter training, and you test on the 1/3 that you haven't seen, or you pretend you haven't seen, or you left out, right? Yeah, so depending on your total data. So this one, you can evaluate your error rate on the samples that are left out. Okay, so there are a number of these algorithms. We'll try to kind of briefly explain them. Online, there are a lot of lectures on this. I think they're actually quite well explained. Let's look at a situation. So in some of the examples people look at, I love this UNC Chapel Hill have a STAT115. They have a very good example. Supposedly, you try to use the size of the mouse to predict the weight of the mouse. Normally, it's a kind of a linear regression, and you can estimate the slope. You can also estimate the intercept. And you roughly, know they are correlated. If the mouse is big, they're also heavier. However, when you have intercept, sometimes it's hard to interpret, which means if the size is 0, the mouse will have some weight, or even you have negative weight, right, which is hard to explain. Therefore, they have some, instead of having the linearity is basically can keep going to positive infinity or negative infinity. So instead, we use a logit function to convert the original linear function into a likelihood ratio or odds ratio, which is the probability of one over the probability of the other. And so this way, we kind of cap the range of this ratio to be between 0 and 1. Because in the classification question, like cancer normal prediction, we are trying to just predict, is this patient cancer or normal, right? And so you can imagine between 0 and 1 as a probability whether this patient is going to be cancer over the probability that this patient is normal, right? So that's kind of capped at 0 to 1. Yeah, so you can imagine this thing also can have a intercept and a slope. And you basically it's just do I have this? Yeah, so each value coming in. So supposedly we only have a single variable. You can also have a intercept and the slope, but then at the end we are trying to calculate this as the using this exponential function in here. Yeah, so you can imagine if this value is super big, then we say, okay, it's almost certainly going to be 1. But if this is really, really small, we say it's almost close to 0, but it never really actually get to positive infinity or negative value, which is harder to interpret, right? Between 0 and 1, it's really easy to interpret. So let's look at a real example. Supposedly, we have the hours you studied on an exam to predict what the probability whether the student will really pass the exam. And you just look at all the students, say in this class, you look at how many hours they did the exam, and you look at their grades, and you plot them on this figure. And you can see here, these are the hours they studied, and these students failed and these students passed. So overall, you can see when the students don't study, they are more likely to fail. But if they do study a long hours, they are likely to pass. It's not perfect. But now we try to do estimate this particular curve. What's the intercept? What's the slope? And if you run the logistic regression using just this single variable, it will estimate this for you. And the p-value actually is significant. Which means, so it's 0.0167, which means, if you study more, it is more likely you are going to pass. You can look at the figure and you can already see that. And so if I give you a particular student, if they studied at certain number of hours, you can just plot in that number of hours and into this equation and calculate. And if this basically it's an odds ratio of probability of passing versus probability of not passing. Therefore, if this final value is over 0.5, you will predict the student as passing. But if they are not, it's below 0.5, you will predict the student as failing the exam. Of course, depending on the specific value, you have either a lot of confidence towards here, like this. If a student study this much, you have a very high confidence. Whereas if they only study this much, they will only be kind of barely passing the exam, right? So it's pretty intuitive. And the nice thing about this also, there is also kind of a decision boundary, which is how many hours do you think, the student will have a 50-50 chance of passing the exam? Based on this this function, you will know the decision boundary is when this term is 0. This exponential of 0 is 0. Is 1, and so 1 over 2 is 50-50, right? Yeah. So how do you get this function to be 0? You can try plot in the intercept and plot in the number of the slope, and then you will get basically the student, if they study about 2.71 hours, they have a 50-50 chance of passing the exam. And you can look at this. This is, roughly, this should be exactly 2.71 hours. Okay, so that's a logistic regression. This is only if we use a single gene to predict whether the patient is cancer or normal. In real logistic regression, it's kind of many variability, many genes you're considering, and every gene is given a coefficient. And you're trying to predict, y is whether the patient is cancer or normal, and there is this intercept, and then there's like a gene 1 coefficient, gene 2 coefficient, gene 3 coefficient. Every gene is given a coefficient, and the logistic regression will estimate a slope based on all the data you give it, and then give each gene a different weight to give you that good separation. And so, so in this case, you can see here, this is in intercept, and we are selecting, gene 1, gene 2, many different genes, and each is given a weight to make the prediction. And so you probably don't want to use all of the genes to estimate the parameter, because that would be too many parameters. Very often when I ask people, we ask people to train a parameter or train a classifier, we have 20,000 genes on this array. And very often you're lucky to have, say, a few hundred patients for cancer versus normal to train the classifier for predicting the new guy. And if your classifier has 10,000 parameters with a weight on every gene, you are very likely to overfit your data, right? So you want to kind of reduce this. how do you find the subset of genes whose expression collectively can predict whether this new sample is going to be cancer or normal? And you try to estimate all the coefficients that you assign to each gene from the training data, and try to make the prediction. And so this kind of goes to a feature selection problem. You can, yes, Jed. Yeah, that's exactly what we're going to talk about. Yeah, so which genes go into this logistic regression? You can imagine the more genes I include, the better it can fit my current data, but it's likely to overfit and perform very poorly on data you haven't seen. So supposedly, this one is, supposedly my data look like this. The underfitting, in this case, I only have very few, if you have a line, you have very few parameters. It can, roughly fit, but not so great. But if I include more parameters, I can fit slightly better. But if I include a lot more parameters, now this is, you can imagine, in order to draw this curve with parameter, you need a lot of parameters. It will fit your data perfectly, but it's unlikely to be the real trend of the data, right? So what is the trade-off? How many genes do you want to select? This type of problem is very typical whenever you have feature selection situation. And so regularization can be used to impose penalty. So basically, every time I add a feature, one extra gene, I need to make sure that it's reducing my error a little bit. So you can imagine this blue curve is what my prediction is, and sometimes it's still not perfectly fitting my original data, and that difference is your error, right? It's how good is your prediction approaching your final data. And so you can imagine this is measuring your error, right? What is the, on every point, this is the model prediction, this is the actual observation, that distance between them is your error. And so this is kind of sum of error between your model and your observation, right? And then this beta is how many parameters you are trying to estimate, the coefficients. The coefficients you are going to provide. And so there are two ways to do this penalty. You try to, basically you can imagine if I have just one gene, there will be just one coefficient, or like you have a beta 0 and beta 1. You have the intercept and you have first gene coefficient. But if I have to consider two genes, then this parameter will be bigger. And basically that will add to this term, and your error, your total kind of penalty will be bigger. So you can imagine as I increase the number of parameters, this term will be bigger, but this difference between your observation and your model, the error sum of square will be smaller. And so you try to balance the two, right? So basically, if you have to add another gene, you make sure that this gene adds some penalty, but then you are reducing the error enough. And there are two different approaches. And so the L2 regularization is each coefficient, you take the square of the coefficient and you sum all of the coefficients together, and you estimate a single parameter in here. But L1 regularization is you take the absolute value of that coefficient, you add them together and you penalize. And so they're actually penalizing different things. So if you're trying to penalize this, you can imagine very often so you will actually, it's computationally efficient. Actually, there's a very, very good analytical solution for this. With ridge regression though, basically every gene, or many genes will be assigned a weight. If you give it this many genes, it will give pretty much all of the genes a weight. Whereas with L1 regularization, it will actually give you a very sparse output just to reduce your total number of parameters. And so, for example, in the microarray setting, you can imagine you do it in a greedy way. You start with the gene that has the best separation between cancer and normal. And you add a second, you check every second gene, then see whether it reduces your error. And then you add a third gene, you try every gene as a third gene, the fourth gene, and so on. And every time you add, you can see whether, depending on whether you are using L1 or L2 regularization, it can reduce your error, but add penalty to that additional parameter. So very often, people try different things. You can try Ridge, you can try Lasso, and see which one in the existing data give you the best performance using cross-validation. Okay, then you can see whether it does a good job. Questions? Sam. You can imagine if you use a stepwise regression to do that selection, it's kind of greedy. You'll pick the one that has the best prediction, then the second guy will not have a chance. It will just be zeroed out. Yeah. Okay. Yeah. So there are statistical features or packages that already implemented this. You can just run this. You will select the genes, and then it will give the genes different weight to make that final prediction. Okay. That's I'm trying to